Today I'll talk to you a little bit about this, this 20 or 30 year long, 30 or 20 years and a $1 trillion long path that's led to our current understanding of carbon nanomaterials. And I'll talk to you a little bit about our work and where it suggests that that path should go. If you think about the materials around you and what gives them the properties that they have, it's really two factors, right? It's what they're made out of, the atoms that they're made out of, and the way that those atoms are arranged. And carbon is so fascinating because it's, if you take all of these different structures, you've eliminated one of those factors. They're all made out of carbon, but it's just the way that the atoms are arranged that give them these incredibly diverse properties, more so than any other element. If you think about the two maybe most familiar forms of carbon that have been around for millennia and used and enjoyed by humans, is diamond and graphite, right? And these materials couldn't be more different than each other. Diamond is transparent. It's the hardest material that we know of, and it's an electrical insulator. Graphite is black. You can't get much blacker than graphite. It's very, very soft, and it's electrically conductive, especially along its basal planes. So it's really a fascinating element to work with. And some of these incredible properties are manifested in these nanostructures. So these kind of superatom structures were discovered in the mid-'80s. And it wasn't long after the processes for synthesizing these superatom structures that we started to be able to control growth of carbon nanotubes, which are usually straight, but this figure shows you some of the nice structural aspects of carbon nanotubes. And I'm really going to focus on these carbon nanotubes because, as this next slide says, they really do have these tantalizing properties. I talked about this 20-year-long path. And this is the fruit of that 20-year-long path at this point, is this knowledge that carbon nanotubes have these incredible structural properties. They're stronger and stiffer than any other material, and their low density makes their specific properties, especially their structural properties, just incredible. In addition to these nice structural properties, they have attributes that make them very multifunctional, very low electrical resistivity and very high thermal conductivity. So these materials, they're so appealing to a material scientist. And if you don't know much about carbon nanotubes and this slide intrigues you, I'm guessing you might, on your own, go use Google. And if you type in carbon nanotubes in Google, Google will send you to Wikipedia. And there's a very nice entry about carbon nanotubes on Wikipedia. It's very long, many screens, at least on my tiny computer, many screens long. And everything I read was true when I looked at the entry recently, but I was shocked that this is the real length of the current applications. Now, how on earth could a material with these kinds of attributes have this miniature list of applications? And I highlighted basically the summarizing applications for this material. And it's maybe hard to see from where you're sitting, so I did a pictorial summary. Really, it boils down to some excellent mountain bike handlebars, a boat, a prototype boat that I didn't really understand the purpose of, and some sporting goods, baseball bats and golf clubs. And even if you're a sports enthusiast, it's hard to buy into the idea that all of that money and all of this effort from some of the world's most intelligent scientists, not to toot my own horn, this is all you get for all that investment. It just seems heartbreaking. And I started to think about why is that the case? How can that possibly be the case? Let's look at a specific example. So I talked about the thermal conductivity of carbon nanotubes. And we and others have measured the thermal conductivity of individual carbon nanotubes on systems like this, microscopic systems, where there's an individual carbon nanotube suspended over a heater and a cold plate. And you make some temperature measurements, just like you'd measure a copper rod, but on a much smaller scale. And you could see over this really broad temperature range, these carbon nanotubes have incredible thermal conductivity, way higher than diamond, which up until recently was well known as the material with the highest thermal conductivity. And the reason, even though they're made out of the same atoms, is that there's a difference in the way that they're bound together. And in carbon nanotubes, you have an extra bond an extra carbon-carbon bond that gives you extra stiffness, which helps propagate waves through the carbon nanotube, which is how heat is conducted. There's no electron contribution in carbon nanotubes. So this is great for a single carbon nanotube. It's got this amazing thermal conductivity. It's hard to use just one carbon nanotube in anything that you can touch or make anything out of. So what do? Well, why not mix them in with something else? Mix them in with a polymer phase and make a composite. This is great. There's some really fantastic things about using something like a carbon nanotube in a composite. If you use something spherical, like let's say silver is a metal with the highest thermal conductivity, and you had some spherical particles which you can easily buy, you would need about 20% or more volume percent before you could really see an increase in the thermal conductivity, a very nice increase. With carbon nanotubes, because they have such a high aspect ratio, that is, their diameter is so much tinier than their potential length. We can grow carbon nanotubes that are like a millimeter, even a centimeter long, but their diameter is still tiny. It's like on the order of several or less than 20 nanometers. So you can have this very high aspect ratio. For this data that I'm showing you here, the aspect ratio is 2,000. So the nanotubes are 2,000 times longer than they are in diameter. And what we can predict just based on simple geometric arguments that work for composite materials is that we should get an increase for just 1% of a carbon nanotube increase. We should get a 30 times increase in thermal conductivity for a polymer composite material. And that's pretty amazing. You put a tiny bit of this fairy dust in this material and you have this really multifunctional composite. It'll still probably have enhanced strength and other polymer-like properties, but enhanced thermal conductivity. What was disappointing was that what happens in reality is about a factor of 2 increase by adding these carbon nanotubes. And it's disappointing, but it's not really surprising. For a long time, we've understood the concept of interfacial thermal resistance. So this is the first paper that reports on interfacial thermal resistance. Keesum, their English was less than perfect. They say that the thermal resistance at the surface was relatively very considerable for these supercritical helium solid experiments that they were doing. But it is relatively very considerable, and it's best shown in this simulation where we've got a single carbon nanotube embedded in this polymer matrix, and we've applied power to the carbon nanotube and made it hot. And what you see is that you've got the temperature of the carbon nanotube. This is like an axial profile. So if I measure the temperature at the edge of this carbon nanotube and go this way, it's like going along this axis. There's this huge temperature drop. It's 120 K just over this tiny space. Like we're talking about a few atoms worth of distance. So it's this huge temperature gradient. The heat can't get out of this carbon nanotube. It flows superbly along the length of the carbon nanotube, but it doesn't go anywhere into this polymer matrix, which is really what you want it to do if you want to have like homogeneous high thermal conductivity. And the reason why we had, and that's called thermal interface resistance, because there's an interface between the nanotube and the polymer, and it's like a barrier. It won't let the heat out. And there's 2 reasons that happens in these carbon nanotube-based composites, or in even carbon nanotubes to carbon nanotubes. The same thing happens, and there's 2 reasons for it. One is that carbon nanotubes are essentially chemically inert. They're not very reactive. There's always a gap. We call it a van der Waals gap between the carbon nanotube and whatever else you try and put it in contact with. And that gap, as you would imagine, acts like a huge barrier for these waves that are propagating through these materials. It inhibits their heat flow. If you could somehow, this is simulation work, if you could magically make covalent bonds between this carbon nanotube up here and whatever other more ordinary engineering material you had it in contact with, if you could make covalent bonds and control the number of those bonds, you could increase, this is the inverse of interface resistance. This is interface conductance, so bigger numbers are better. The more covalent bonds you have, like down here, this is the number of covalent bonds, the more of those bonds you have, the higher that conductance is, the better heat propagates from one surface into the other. So that's one, is this kind of chemical inertness, this lack of intimacy between the nanotubes and whatever they're in contact with. The other is the first thing I talked about, was how great and remarkable carbon nanotubes are. Those remarkable properties make them unlike a lot of other materials in lots of ways, especially vibrationally, because they're so stiff. Waves propagate much differently through a carbon nanotube. It's very stiff bonds than it does in a more ordinary, floppier material. And that causes some problems. You can see how that's manifested in this kind of simple simulation where there's a heat pulse, and it's propagating through this solid that has one set of vibrational properties. This material has 4 orders of magnitude different vibrational properties. And as that wave comes to that interface, only a tiny fraction of the energy propagates through the interface. A lot of it is reflected back. So this big glob of energy is just coming back. It's trapped in this material, just like the heat was trapped in this carbon nanotube. So we've got to try and overcome these interfacial effects to really realize the utility of these carbon nanotubes. Even a fraction of their utility would be amazing. It would really change the way that we could make materials or make components involving these materials. So I'm not the first one to understand all this. People understood that there were problems making contact between carbon nanotubes and other materials. And the approach that they took, so many people took, was this covalent functionalization, where you strongly bind molecules to the carbon nanotube surface, and those molecules will react well with a polymer matrix or a metal or whatever. You can really tailor. We're good at this. We're good at selecting these molecules, making them attach to something like a carbon nanotube, and make that interface really great at conducting. The trouble is that when you attach these molecules covalently, you do kind of the same thing. This is a simulation. Actually, these simulations are just for one molecule on a long carbon nanotube. And you have the same thing happening here. You send a heat pulse in. You have reflection at just that site where the molecule is. So by functionalizing the carbon nanotube, you enhance its interface. But you ruin the properties of the carbon nanotube itself by breaking up those bonds. Remember, I talked about the difference between carbon nanotubes and diamonds. Is that sp3 versus sp2 bonding. I'm converting the sp2 bonds in this carbon nanotube to sp3 bonds, and the conduction is poor. So I'm improving the interface but ruining the nanotube itself. This is not the way to go, and there's other practical problems. It's not thermally stable, lots of these linker molecules, or a whole host of reasons to not use them. And so what we decided is to try some metals. Let's use some metal particles or atoms and join these carbon nanotubes. Now, if I join 2 nanotubes together, like in this simulation, I still haven't really done what I want to do. I want to make that list on Wikipedia really long, and 2 nanotubes isn't going to do it. So we thought about how to make these carbon nanotubes into macro scale assemblies, and I have some examples. I have some carbon nanotube paper, which it's not the white stuff, it's the black stuff. It's a lot easier to handle if you sandwich it between 2 sheets of real paper. And I have some carbon nanotube yarn that we made. And this is what happens if I get bored on a Saturday afternoon. I ask my wife to start doing strange things like sew together the carbon nanotube paper with the carbon nanotube yarn. This is actually in the picture. It's functionalized carbon nanotube paper and yarn. So we've attached metal particles to the nanotubes and made paper out of it. We've attached particles to the nanotubes that go in the yarn, and before it was yarn. I'll show you how that works. So this is kind of special nanotube paper and yarn, and you can handle it just like you can a regular like fabric and thread. And she sewed 2 pieces together, and I cut it, and I asked my son to go get a circuit set, and he built this light circuit, and I said, all right, let's pull off one of these rigid pieces and insert this stuff, and the seam is perpendicular to current flow, and we still get the light bulb to turn on. And my son, he said, we were just about to go backpacking, and he said, this is awesome. I could bring my circuit set backpacking. And I thought, well, that's nice, son. You know, but when I thought about it, he's onto something. I can make a lot of money. All these things are really just very specialized portable circuit boards, right? I mean, in a simple way, that's really true. What if I could take this fabric and thread and make tents And instead of just putting ordinary particles, I put thermoelectric particles. These are materials that turn heat into power. So imagine what I could do with that. Imagine how many lives would be saved in these engagements that we've had transporting fuel if less fuel had to be transported. There's so many kind of neat things that you can do with these fun things that really are just these flexible, lightweight, portable circuit boards. One of the simplest manifestations, a very nice application for the thread, if we can make it electrically conductive enough, is to replace copper on these airplanes, right? So there's like 3,500 pounds of copper on a 747. I did kind of a rough back-of-the-envelope calculation for I think for a 1,500-mile flight, that turns into about $1,000. So that's I think the airlines would be very pleased to be making that much more money on every flight if they could, at no sacrifice for performance. You know, most of that copper wire is for the little television in front of your seat, just as a matter of fact. So this is kind of a nice idea. So this is our approach that we've taken to do this work. Is we think and we do some simulations about what kind of functionalization is going to get us the most impact on an individual basis. So this is like for a simulation of 100,000 atoms, which is kind of computationally expensive. It takes a long time. We can do this and understand some fundamentals about what's happening at these interfaces. And then we want to apply what happens on 2 nanotubes and 2 junctions. We want to make millions of these junctions, actually maybe 1 for every $1 in the Department of Defense budget, and make these materials on kind of a macro scale and turn them into something we can use like thread. So how does that work? Well, unfortunately, nothing's ever very easy. We're a little bit at the mercy of nature. So I'm showing here, this is just a mess of carbon nanotubes that we can turn into paper or yarn later. But we've attached different kinds of metal nanoparticles under identical conditions. So we looked at gold, nickel, and titanium. And again, the conditions are the same for each of these processing experiments. But the morphologies of the particles are really different. So you can see the gold really clearly, especially at high temperatures. You've got these big islands of gold, the white stuff on these dark nanoparticles. For nickel, you can make them out. And for titanium, you really got to squint to be able to see. These are like the emperor's new nanoparticles, right? I can tell you that they're there, and maybe you'll believe me if you're really smart, but maybe you won't. And really, we need another tool besides an SEM to be able to see them because they're so small. And we have, but this is a nice figure, and it just shows you that there are some physical limitations to this approach. We need the particles to be a certain size to get the kind of functionality that we want, but the size is limited by nature. And so we thought about how this works, and we realized that there's a trend. It's really a simple trend. There's a binding energy of each element, how much energy it takes for the atoms to be combined or separated. How much energy does it take to separate these atoms? And that energy dictates how big those islands are, how many of those islands are. So we thought about the parameters that drive that and came up with some ways to make gold particles look just like titanium particles and vice versa. So we overcame that barrier. And that's great because now this is how we do it. This is how we make the yarn. So we start off, this is a 1-inch by 1-inch square silicon wafer that has a vertically aligned array of carbon nanotubes growing on it. So if you look at it with an electron microscope in profile, it looks like this. So all of these are these vertically aligned carbon nanotubes. The silicon is way down here. These nanotubes are 300 microns long in this case. And you can see this transparent black web. This is about a foot long. And what it is it's composed of these nanotubes. They pull off of the substrate, and they hold on to each other through these kind of weak van der Waals forces. But you can pull them across. Remember, I said these nanotubes are 300 microns long, so this is a whole long line of these carbon nanotubes. There's a bunch of carbon nanotubes making this foot-long line. And then I can wind it on one of these bobbins. And that's these silver things. There are 4 bobbins with different kinds of nanotube yarn on there. So this is great. What we want to do is we want to attach the metal nanoparticles on these nanotubes before we spin it into the fiber. And then we have this homogeneous distribution of these nanoparticles all through this yarn. So this is demonstrating some of that control we have. These are all gold nanoparticles. These are pretty large. These are like 30 nanometers in diameter, and these are like 3 nanometers in diameter. So we made different yarns and looked at some of their properties. This, driving the metal through that 300 micron thick array of nanotubes is not necessarily straightforward, but we developed a process to do that. Basically, all of the metal is ionized, and it has a lot of kinetic energy, and we drive it in to these arrays. And actually, it has so much energy that it'll impact. Well, it's easier to see here. This is we borrowed this idea from the microelectronics folks. If you use low energy particles, you get these kind of umbrellas on top. They grow together and keep any metal from penetrating deep inside these trenches. But if you use atoms that have enough energy, you can actually spread the metal out that's on the bottom and on the sidewalls and get it to redeposit from the bottom to the sides. And it'll also break up these features on the top. So by using this highly energetic ionized plasma process, we can penetrate deep into these forests and make these beautiful homogeneous gold nanotube yarns. So this is our microscale test apparatus that we use in an SEM to measure electrical conductivity and strength and thermal conductivity as well. We can cut this fiber. So this is one of these pieces of carbon nanotube yarn, and look at it in cross-section. And so the nanotubes are these light phases, and these black phases are gold nanoparticles. So I can cut this thing anywhere and see the same kind of distribution of metal and nanotubes. So I have this true composite material. And you can see what happens in terms of the properties. I have this here in surface area increase. This is basically just a function of how small those particles are. The smaller that they are, the more surface area that they have, the higher my thermal conductivity is. And that's pretty interesting. You see some other things too. There are changes in strength. We've actually increased the tensile strength of these by adding metal. We didn't think we were going to be able to spin them at all because I described to you how they're spun. They rely on those weak van der Waals forces between nanotubes to pull each other off of that substrate and maintain continuity as they're spun into yarn. We thought the metal would interrupt those forces and make it weak, maybe even too weak to spin. But that wasn't the case at all. We actually had this increase. And there's a reason for that. We're in this regime of length and aspect ratio of the carbon nanotubes. The laser is kind of weak right now. But this regime where friction, intra-tube friction, really dictates the strength. And you can imagine how making the tubes bumpy by really increasing the surface area increases that intra-tube friction. We did some simulations and some very fundamental measurements of thermal conductance. And we did it for some elemental metals and also for some metals that react with carbon surfaces that are very reactive. And what we found is that we can understand how these metals improve intratube thermal conductivity by understanding their vibrational properties. So these are some Latin or some Greek letters, but really this is representing how well we're matching the vibrational properties of the nanotubes with the metals that we've selected. And you can see this is thermal conductance. Again, big numbers are good. The higher the thermal conductance, the better the heat transfer is through these materials. So we see that the better we match the vibrational properties of the carbon nanotubes with the particles that we select, the higher the thermal conductivity is going to be. But we do see metals like titanium and chromium kind of rising to the top. And we are chasing a hypothesis here that it's due to carbide formation, which we can see in our growth process. We can see that we form these carbides. So maybe we're forming these nice kind of covalent bonds like in that simulation that I showed you before with the nanotube and that other surface. The more covalent bonds you had, the better the interface conductance was. We're trying to tune the thickness of that carbide layer that's grown on these interfaces, and we're trying to tune it to match the great results that we're getting from our simulations that tell us just how thick that carbide layer needs to be to optimize thermal conductance.